Thank you for watching my talk today. I'd like to spend a few minutes talking to you about an analysis of the PICUP collection of exercise sets, specifically looking at the strengths of the current collection and areas for development in future exercise sets. So first, I'll give you an overview of what the PICUP collection is. We'll take a look at the challenge level of these exercise sets. What can you expect your students to be facing in these activities? Then we'll take a look at the features of these exercise sets. What is their contents like? And then we'll evaluate our observations by looking at the strengths of the collection and opportunities for future development. So PICUP, or the Partnership for Integration of Computation in Undergraduate Physics, is here to support physics educators in integrating computation into their courses. This is, of course, increasingly important as it helps students both learn the physics concepts that we want them to learn and also helps them develop valuable research skills. So the PICUP collection features peer-reviewed computational activities written by physics educators. There's currently 62 exercise sets in the collection, which over time has meant an average of just under one exercise set published each month. So what I'd like to do in this talk is examine the questions of what is in these exercise sets and what else do we need in future exercise sets. So to give you an idea of who these exercise sets are made for, each exercise set is tagged with a course level going from high school up to advanced. The majority of the exercise sets are focused, unsurprisingly, at the undergraduate level. That is what the U in PICUP stands for. There's also a lot of cross-listing between first year and beyond the first year. So many of these exercise sets in the middle two bars are cross-listed between the two, whereas very few get listed at the high school level or at the advanced level. Another property that authors are asked to include in an exercise set is the completion time. If you take a look at the minimum completion time in each exercise set, you can see that most of them are designed to be completed at around the 2-hour mark, which makes sense. Most of us use our extended lab time for computational activities, and this time span fits right in that range. Another property we can look at is the word count across the exercise sets. As you can see here, most of the exercise sets fall in at 3,000 words or fewer, so not terribly onerous for our students to read through. Now let's take a look at the contents of the exercise sets. When you open up one of these, what are you going to find? Each exercise set is tagged with a subject area, which is basically what course would they fit in. Many of these exercise sets use one or more specific computational methods. That's actually what the computer code is doing. Each exercise set is required to provide a code template. We'll look at which platforms, the languages and programming environments that the exercise set includes. And then finally, we'll take a look at engagement elements, things like visualization and external data. So first, let's take a look at the subject area. This is basically what course would the exercise set be used in. Each exercise set can be tagged with one or more subject areas. We see that by far the two most popular are mechanics and electricity and magnetism, which makes sense given the popularity of introductory level exercise sets. And these are the two topics that you would have in an introductory course. The number one topic within all of these subject areas is gravitation. Not really a surprise. It's a nice, complete, open-ended problem that you can't solve analytically when things get interesting. And so gravitation, very popular among these exercise sets. Next, we'll take a look at the computational methods employed in the exercise sets. These are specific methods used like Euler-Kromer method, differential equation solvers, Fourier series, integration functions, things like that. What you see is that Euler-Kromer, incredibly popular, used in over 1/3 of the exercise sets, very popular in mechanics-based codes. After that comes numerical integration, also popular because it's frequently used in electricity and magnetism exercise sets, and we saw those were the two most popular subject areas. One of the things that's interesting to note, if you count the number of computational methods used in each exercise set, most of the exercise sets use a single computational method. There's very few that mix and match between these, which is really advantageous pedagogically, since usually these computational methods are new to our students, and so introducing just one at a time is a really helpful way of relieving the overhead in using these exercise sets. When you submit an exercise set to the PICUP collection, you're required to include a code template and a completed code in at least one programming language. Here we see the different platforms that are used. So by platform, I mean both the programming language and the environment in which you're using that language. So for example, IPython and Python and GlowScript are all listed separately because even though they all use Python, they have very different interactive features that instructors may be looking for different pedagogical advantages through. By far the most popular are the Python-based languages, GlowScript, IPython, or Jupyter Notebook, and Python. Not really surprising. If you're here at an AAPT meeting, you're going to hear a lot of Python talk. After that comes Mathematica, also not surprising given how popular that is among our students' math prerequisites. If you count the number of platforms that are used in each exercise set, the vast majority include only a single platform, and then a handful will use 2 platforms. Notice that the PICUP editors recommend including at least 3 platforms, so most of the exercise sets are falling short of that recommendation. Next, let's take a look at the engagement elements. These are all of the extra features that we include in these exercise sets that help students engage with the material beyond simply running the code. So engagement elements include simple things like line graphs and histograms to more emerging visualization techniques like heat maps, or more pedagogically challenging features like incorporating external data or an experiment from the same class. What we see, line graphs, very popular, not really surprised there. That's kind of our default means of visualizing data in physics. 3D graphics is also popular thanks to Matplotlib and VPython, but you can see we have a pretty good variety of engagement elements being used. It's also encouraging to see that many exercise sets use multiple engagement elements. You can see that several of them use 2 or 3 engagement elements in combination with each other. So we see from this data that the PICUP collection is off to an excellent start. There's a good representation of subjects and a focus on analytically intractable studies like gravitation. Most exercise sets focus on a handful of topics and just one computational method. And there's a frequent use of a few methods and platforms, meaning if you are a newcomer to computational instruction, it's much easier to get on board because you just have to learn a few methods and 1 or 2 platforms. There's also a very good use of engagement elements that we can definitely expand upon. And you can definitely find enough exercise sets to teach an entire first year or second year course on nearly any subject. Moving forward, here are some things I would recommend that future exercise set authors focus on. We definitely need more exercise sets at the high school and advanced levels. Part of this may be due to some ambiguity of what we mean by advanced level compared with beyond the first year. Is it senior level? Is it graduate level? What does advanced really mean? We can also likely adapt many first year exercise sets for high school use. We also definitely need exercise sets implemented in more platforms, which is usually a matter of seeking more collaborators. Most of these exercise sets are written by a single author. By including just a second author, we can likely get more platforms up in the collection. We can also explore more intractable problems. Gravitation is great and it's interesting, but what else out there could we start exploring in these exercise sets? We can also expand on some underrepresented computational methods and engagement elements, especially the ones that are of popular demand in industry. And finally, exercise sets could explore more overlap between subjects and also start combining computational methods, especially at the advanced level. So today we took an introductory look at the PICUP collection of exercise sets. It is growing and has some promising features. The challenge level is mostly geared toward the undergraduate curriculum. We certainly do seem to love our Euler-Kromer method and Python, and basically we need to start expanding the good work we're already doing here, especially in terms of getting more platforms and more topics. Thank you again for watching this presentation. I am working on an article about this analysis that I would love some feedback on. If you're interested in giving that a look and giving me some feedback, just send an email to me at the address here on the screen. Thank you so much. Looking forward to the discussion with you.